Korea from La Plata University. He will talk about Cusp anomalous dimension in unequal force economic theory.
Okay, well, thank you very much for the chance of talking here. So, yes, as indicated in the title, what I'm going to be telling you is about how to compute the Cusp anomalous dimension exactly as a function of the coupling in the planar limit of n equal 4 super Young mills. So, this is related to a series of articles I written in collaboration with Johannes Hen, Juan Maldacena, and Amit Sever. But I'm going to be focusing on this one, in which we study the problem using integrability. So in 3 lines, the outline of the talk is what I'm going to be describing, why it's interesting, and how I'm going to do it. So, well, the object of the study is the Cusp anomalous dimension, or to be more precise, the expectation value of a Wilson loop with a Cusp angle. Well, I mentioned a few motivations. I mean, this is an interesting quantity in any gauge theory because it is related to the diverse physical observables. And the way I'm going to be computing this exactly is using integrability. It's a very indirect method in which we deform the Wilson loop by inserting an operator. And once we have an exact description, this L means the size of this deformation. When we have an exact description in L, we are going to send L to 0 to recover the original Wilson loop without any insertion. So I should emphasize again that I'm going to be talking about the Cusp anomalous dimension in n equal 4 super Young mills theory, which is the gauge theory of the prototypical example of the idea CFT correspondence. And I'm going to be working in the planar limit. So, because it's only in the planar limit that integrability has been observed so far. So, well, as I said, what I'm going to be describing is the expectation value of a Wilson loop. If such a Wilson loop has a Cusp angle, so a sudden turn at a point along the loop, it's been known that because of this Cusp, the expectation value develops a logarithmic divergence, and precisely the coefficient of this logarithmic divergence is the anomalous dimension that develops this operator. So of course this is going to be a function of the angle of the Cusp, and of course a function of the coupling. So, but I mean, as I said, I'm going to be considering this problem in n equal 4 super Young mill, and not for this Wilson loop, but for this other one. So in n equal 4, there are also these adjoint scalar fields fields in the actual representation. So we can consider that this Wilson loop corresponds to a quark that is also charged under this, or this coupled also to these scalar fields. So we can consider this. And the reason for considering this, for adding this extra term in the Wilson loop, is because if we consider, let's forget it for a moment about the Cusp, if there was just a straight line, if you take this, so this is a vector that in principle could be a function of the parameter of the curve, of the contour. But if you take it to be constant, this object is, we know Cusp is a half BPS operator, and in that case there is no Cusp anomalous dimension. So anyway, we are going to not consider the BPS case. So we are going to have these 2 half lines with an angle. So in principle we can take n to be constant, but to be different in this half line and in the other half line. So and this just by picking 2 different constant vectors, we can define a second Cusp angle, and we can refer to this as an internal Cusp angle. So in n equal 4, the Cusp anomalous dimension of such a Wilson loop is going to be a function of 2 angles. One is this geometrical Cusp, and the other one is this internal Cusp. And of course, it's going to be a function of the coupling and and the rank of the gauge group. So this is what I would like to describe exactly.
Can you remind us the thing that people always used to call the Cusp anomalous dimension related to twist-2 operators and their leading scaling?
Yes. So
that one special value of
yes, exactly. So that you recover it when you take a boost angle. So you consider like a bar phi equal to I phi, and you take this bar phi to infinity. So this is what people call the Cusp anomalous dimension in the context of twist-2 operators. So that's right. So that's also an interesting. I'm going to mention this later. So this quantity corresponds to that one in this particular limit. So, well, why is this interesting? Well, in principle, I mean, if you think of this as a trajectory of a quark, so there is a sudden change in the velocity, so there is going to be radiation, and this quantity is related to the power that is emitted by this quark. It is also related to the IR divergences of certain amplitude of massive colored particles. But maybe the most important, I mean, or at least what I think it is the most interesting motivation is that this Cusp anomalous dimension is precisely the quark anti-quark potential for the theory defined in the 3 sphere. So typically the potential between two particles, two charged particles, is computed by considering a Wilson loop in a very elongated rectangle, right? So let's call this the spatial separation, and this is a temporal separation, demanding that T is much larger than R, and the expectation value of such guy is what give us what it is the quark the static potential. So I mean, it doesn't look like it is this, but if you take the plane to cylinder map, I define the logarithm of the radial distance with the time in this cylinder. These two lines are mapped to parallel lines in the cylinder. So we're now, if you have a cusp, these lines are not antipoidal, and they are separated by pi minus phi. Moreover, you see that, I mean, the UV cutoff is mapped to a past infinite in this time, and the infrared cutoff is mapped to a future infinite. So essentially, this logarithm of the cutoff, what it gives us is the temporal extension of these two lines, and then what we were calling the gamma cusp is precisely the quark anti-quark potential. So it is in this cylinder, but if we take the limit in which this delta, or when phi goes to pi, this is also the quark anti-quark potential in flat space. So this is another interesting limit. So I'm not going to be talking about this, but let me just mention this other result. So as I said, I mean, if the Wilson loop, if the line was on a straight line, this is VPS, but you can introduce two cusps, and if they are the same up to a sign, this is still a VPS object, and there is no cusp anomalous dimension. So there is a situation in which you can call it near VPS, or near supersymmetric Wilson loop, in which these two angles are almost the same, up to a sign. Then you can expand the gamma cusp in powers of these theta and phi angles. So to live in order in this near VPS situation, I mean, what would you like to know is this H function. And it happens that, and this is without using integrability at all, this is just using the exactly known back-in expectation of the circular Wilson loop, which was computed using localization techniques by just taking, I mean, this function h that gives us the anomalous dimension in this limit is just a derivative of this known with this function, which is known exactly both in lambda and in n. Anyway, we are going to be interested in the here in this. So this is not absolutely. So this is the exact answer. This is just the well, that is written here. So this is just the 1 over n, the large n approximation. And we're going to be interested in this limit because in this limit we can reproduce the same computation using integrability. So we are going to use, I'm going to use this result just to test my final system of equations. So the method I'm going to present is pretty indirect, as I said. So I will start with a Wilson loop, but I'm going to consider a deformation by inserting a local operator. So these letters here means different fields of n equal 4 superdiagonals. So they are action fields, so they are matrices, so you can naturally write them as a chain of fields. So they are all evaluated at the same point along the contour. Well, and then you can provide a description of this, the expectation value of this operator, by diagonalizing a spin chain associated to this open chain. And since this problem turns out to be integrable, we can solve it using the Vere ansatz. So I'm going to give more details later, but in order to describe this problem using the Vere ansatz, what you need to know is the exact reflection matrices and bulk scattering matrices. So these pictures are not space-time diagrams. They represent the. So here, for instance, I'm going to take like one of the fields to be the vacuum, and the other ones are going to be impurities in this vacuum. So this represents the trajectories of impurities in the chain. So this is not a space-time. This, or if you want, this spatial direction is the spatial length of the chain. I added indices because these impurities can be of different sorts, so different values for this index AC are different kind of impurities in this chain.
So inserting it in a Wilson line gives you a specific boundary condition?
Exactly, so the Wilson lines are going to provide us what the boundary conditions are for this, and eventually what the reflection matrices are for this open spin chain. So, well, but I'll say later, I mean, this Vere ansatz description is only going to be valid exactly as it is when this operator I am inserting is very large. And I said eventually I wanted to take it to 0 size. So there are a few things we had to do. Well, first we also, I mean, here in the picture I was not introducing a cusp, but the cusp amounts for just the global rotation of the of the boundary reflection matrix. So this is just a rotation matrix which is going to add a few simple phases depending on the angles. But the most important thing is that I would like to describe the spectrum of such open chain exactly as a function of L, and in order to do that I'm going to present a thermodynamic Vere ansatz. Once we have control of finite size corrections, we can describe, for instance, the energy of the vacuum of this open chain. So the Casimir energy, the energy how it is corrected when you consider the finite size. And if you take the limit L going to 0, this is just the size of the insertion disappears, and what you are left is with just the cusp, the Wilson loop with the cusp, and this is what we wanted to compute. So we would like to compute.
So there's some boundary contribution to the energy? I mean, the ground state energy resides in the boundary as well as in the chain? Or
well, I mean,
you would think if you take the length to 0, the energy would go to 0.
Yes, but I mean, typically, if you have boundaries, you would imagine that it receives, I mean, the energy receives a correction when the boundaries can talk to each other, can interact somehow. And this is what the TVA computation is computing. And then the limit of that interaction when it goes to 0. You could think, I mean, you could ask, why do you want the scattering factors, reflection factors, if after all you are just describing the vacuum state when there are not impurities? But you will see that the thermodynamic Vere ansatz depends on analytic continuation of these reflection factors and bulk scattering factors. So before I start, let me just flash what the final answer is going to be. It's going to be, well, this anomalous dimension is going to be given as an infinite sum of integrals of the logarithm of these y functions. And these y functions have to be taken to be solutions of certain TVA equations. Schematically, they look like this. So the dependence on the angles are pretty simple. These are just like some factors in the reflection matrices. Well, this is the size. Well, I mean, in order for this to be gamma Cusp magnetic, I should take L to 0. This is the dispersion relation of these some particles, and this kernel here, it has to do with the bulk scattering matrix, and this is a convolution. So you see, it's a coupled integral equation for these y functions, but what we're going to do is just to compute everything that enters here exactly as function of the coupling, and then it matters just how to solve this equation, and then you can get the answer exactly as a function of lambda.
You don't have to, I mean, TBA for the spectral problem involves a sum over some funny set of states.
Oh yeah, that's what this is a schematic. I will show you.
Okay,
I mean, but I mean, the idea is something like this. So of course you have much more y functions than this, but this is just a schematic so far. So I don't know, if there are no more questions, I'm gonna go with a more technical description. So as I said, I mean, instead of considering just a Wilson loop, I'm gonna consider this deformation by inserting some operator at some value tau of the parameter. And as it is done for instance, single traces, you can just identify different Wilson loops with different insertions by different states of an open spin chain. For instance, in this case, whenever you have a Z field, you have a spin up. Whenever you have a Y field, you have a spin down, so on and so forth. Then, if you compute the expectation value of such Wilson loop with two of that insertions, this reduces to some. I mean, you have to renormalize these operators you are inserting, and then there is a mixing you have to diagonalize. So this mixing problem reduces to some diagonalization of a spin chain with open boundary conditions. So this was done by Drucker and Kawamoto to one loop in certain sector. So, and well, this problem in that case, and could be in the more general case, can be argued to be integrable. If you have an integral spin chain, you can solve it using the Bethe ansatz. I'm not going to give details, but the bottom line of the Bethe ansatz is that you can compute all the eigenstates of this Hamiltonian that solves the mixing problem and gives you the exact expectation value. You can compute all the eigenstates in terms of just scattering matrices, in this case. So you can have the bulk scattering matrices for when you have the scattering of two or more impurities here, or you can have a reflection matrix when one of those impurities is reflected by the boundary.
That's only if the spin chain is long enough.
Yes, exactly. So, and then once you have that, you just have the total energy, which is going to be, energy means anomalous dimension for us, it's going to be just the sum of the individual magnons. And if you put two boundaries, there are some boundary conditions which are called the Bethe equations. In this case, look like this. So they involve both the scattering and the reflection matrices. And then if you have some number of magnons, let's say m, you have to solve for m equations, and then you plug the solutions in this dispersion relation, and you get the exact anomalous dimension of such state. So, but what are those dispersion relation and scattering and reflection factors? So, well, in principle, as Drucker and Kawamoto did, you can work it in perturbation theory. You can work them out just by computing these 2 points. This Wilson loop with two insertions, and this amounts to just do Feynman diagrams like this one. So you see here, I was trying to show that, for instance, the impurity can be moved when you act with these vertices, and then you have to diagonalize somehow this mixing. But if you work perturbatively, you could do it at one loop in certain sector. If you are brave, you can maybe try to work it out the two-loop computation. But in order to have an all-loop answer, we need an all-loop expression for all these three quantities. So
the S matrix presumably should be the same.
it's exactly the same. Yes. So we only need also the dispersion relation. We also need to compute what the reflection.
Additional.
That additional. So let me just review what the. So well, it all comes from an idea I think by Weissert, 2005. Just using some symmetry arguments. So these are the symmetries of the vacuum state when you have only set fields with no impurities. So those are the symmetries transformations that leave the scalar, the single scalar invariant. And if you demand that excitations transform in representation of this symmetry, you can fix the dispersion relation to be like this. And if you demand that the scattering matrix is preserves this symmetry, the matrix part of this 2-point S matrix is fully fixed. So those are known functions of lambda up to an overall function you cannot fix with this argument, right? Then, I mean, Yannick proposed that if you, moreover, I mean, you demand that this scattering matrix satisfies crossing symmetry. Crossing symmetry is something that relates the bulk scattering of particles and antiparticles. This is going to impose a condition on this unknown dressing phase. And later, a solution consistent with the bilateral explicit weak and strong coupling computations was found for this unknown boundary bulk scattering phase. So as Nick mentioned, we only need to do the same to compute, or something similar, to compute what the exact reflection matrix is. Maybe it's a bit technical, but so let me, as I said, so in these bulk magnons were in the fundamental representation of two copies of SU2/2. So that's why I put the two indices. One is for the left factor and the other one is for the right factor. And now we would like the reflection to preserve some residual symmetry, which is not going to be the original SU2/2 square. Because this is the symmetry of the vacuum, but we also have a boundary, which is those are the symmetries of the Wilson loop. So if you, the only symmetry you want to be preserved is the common symmetry between these two groups, and this is just a diagonal copy of a diagonal combination of the generators of these two copies. So typically these left and right indices, they don't talk to each other in bulk scattering matrices, but they are going to start to mix with these reflections. So typically, so you have a magnon that has these two indices, A and A dot, and after reflection you're going to have something with the momentum has been reserved and you have some other indices. So it turns out that this bulk magnon with these two indices becomes, when you consider it as representation of this residual symmetry, as a pair of magnons of this diagonal smaller group. And more precisely, it becomes a pair of magnons with momentum p and minus p. Right? And then it's very natural that when you demand that this symmetry is preserved in this reflection, what you get is precisely the same matricial structure as you got for the bulk scattering case, just by when you evaluate it in p and minus p. This is I added to in order to be more similar to the bulk scattering case, but of course, I mean, again, this argument does not fix the overall scalar. So there is, I mean, I am hiding my ignorance in this dressing factor here. So, and this is the most tricky part. And again, what you could do is to impose some boundary crossing condition with, I'm not going to just present the result. This imposes, again, a condition on this unknown function, dressing function, And we found in our papers a solution to this crossing equation, which is, I mean, this is pretty similar to the expression. I mean, there is a paper by Nick, Hoffman, and Maldacena where they constructed, they written the dressing phase in terms of contour integrals. This is like the DHM version of our dressing phase. Well, I'm not saying, here it is. So here you see there is a some complicated dependence on the coupling. G is just the square root of lambda. So this function, and this p, this x somehow parameterizes the momentum. So there is a subtle dependence on the momentum and on the coupling here. So, well, but as I said, this is subtle because there is the solution to this crossing equation is not unique. There are others, so we wanted to check. And you can check, for instance, if we evaluate our dressing phase in the strong coupling limit. This is like what we get for this new piece. This is just coming for the bulk crossing equation, the bulk dressing factor. And the expression we get for the limit in which the coupling is taken very large is exactly what you get when you do an explicit computation. This
not really very restricted, though, is it?
No, well, but
First coefficient in the expansion.
Right. But I mean,
is there some minimality assumption? That's the normal thing that you would have to minimal number of poles, something like that.
you can analyze it. We didn't, but I mean, another, if you want, another strong indication that this is correct, that this dressing phase, and as we will see, it has a particular pole in the mirror theory, which was crucial for the TVA to give the correct answer. So, if you want, the TVA verifications are another check of this is the correct. Yeah, but that's right. In this case, we don't have as much as that as there was for the bulk scattering dressing phase. So in this case, it's a minimal check, but it is what we have so far. So okay, so now we could say, okay, now we look at the beta equations and we use the all loop expression for the reflection matrices and the bulk scattering matrix, and you could say, okay, well, now we know the full spectrum for this Wilson loop with insertions at any order in the coupling. That's right, but this is only valid for asymptotically long chains. If the size of the chain, this L, is finite, you need to take into account these corrections. So, and this is what we do with the boundary thermodynamic Bethe ansatz. So the idea is as follows. So consider, I mean, this is the original system in a finite open stripe, and we compute a partition function for certain temperature. So this is, you have to sum over all the eigenstates and the eigenvalues of this Hamiltonian, of course, depending on the size. So this is what we don't know how to compute exactly. So instead of computing this partition function, the physical picture, we are gonna do some mirror trick. So some double wick rotation, which essentially exchanges the notion of space and time. So by doing this double wick rotation, we go to the mirror theory. Now it's like rotating the picture 90 degrees. And now what we have is not a partition function because we don't have periodic conditions in this temporal direction. So we have an evolution from an initial to a final state. And now, moreover, we don't have an open system. We have a system which is periodic, and the periodicity is given by the temperature. We put it in this partition function. And we would like to compute the evolution of this initial state in this periodic system to a final state in a finite amount of time. So, okay, well, here we are talking about these initial and final states, so those are called boundary states. And it turns out they are completely given in terms of certain analytic continuation of the reflection matrices. So that's why we needed to know this guy exactly as a function of the coupling and the momentum in order to analytically continue. So it can be written as the exponential of these integrals of pairs of particles with momentum minus p and p, and the coefficient in this expansion is precisely this k, which remember is just an analytic continuation of the reflection matrix of the physical theory. But remember, we don't want the partition function. What we wanted, let me just write it here. We wanted to compute the Cusp anomalous dimension. That was nothing but the limit as L goes to 0 of the energy of the fundamental state, which is going to be a function of L. So, of course, instead of consider the full partition function, we're going to just take the 0 temperature limit of this partition function. So, in the physical picture, the partition function is just the exponential of the.
Is L an integer?
Yes, well.
The system only makes sense, right?
For yes, in the string theory side, if you want, I mean, for the field theory.
So there must be some assumption about some kind of analyticity in L.
Yes.
I mean, it's like doing, trying to do SU2 or SU3 in large N limit.
Yes, you're right, but I don't have a strong argument to how to think of this as a continuum variable. But you're right. I mean, in the field theory picture, L is just the number of sites, and it could be certainly, it has to be certainly. But somehow this is like if you want, an analytical continuation of this for any value of L, and then take the limit, and hopefully we get the correct answer. Well, let me go on because I don't know how to argue better this. So on the one hand, so if we just take this temperature, I mean beta to infinity limit, so this is just going to be dominated by the energy of the ground state, which is what we would like to compute. But this is also simplified in the mirror theory, because if we wanted to compute this for finite values of beta, we would have again we would need to know the eigenstate of this Hamiltonian, and we will face a similar problem because this is going to be a finite size system, and even so there's another assumption here that when you rotate this picture, what you're going to get for this mirror theory is just the analytic extensions of the bulkhead matrices of this physical system. So we are assuming that the mirror theory is also integrable. But in this limit, so beta gives us the size of the periodic system. If beta goes to infinity, the beta answer description in this mirror theory is exact. The finite size corrections due to finite beta goes away. So this is what I'm going to do. So this is the strategy. So take the beta going to infinity limit, and then so this expectation value of, this propagation from initial to final state in the limit in which we can solve this exactly using better ansatz is going to give us the energy of the ground state, which eventually in the L going to 0 limit is going to give us the Cusp anomalous dimension. Still, this is not straightforward because if you look at the way I written this boundary state, I was using just superpositions of states with momentum minus p, and they are typically not eigenstates of the periodic, the closed Hamiltonian. That they could be eigenstates only the S matrix were trivial, but it is not. So that's so diagonalizing this and considering this the projection of these eigenstates onto these boundary states is precisely what the proper TVA computation does. But before doing that or presenting the result of that computation, I'm going to just assume for a moment that these creation operators that they were used in the boundary state are precise eigenstates of the Hamiltonian, and what this gives as I show later, is the leading finite size correction. So this is, or the Luchter correction, if you want. So if now these creation operators were eigenstate of this Hamiltonian, so this computation simplifies a lot, because now when you act with the Hamiltonian, they just you just have to consider the projection of the two-component particle onto the two-component particle weighted with this phase, the projection of the the component with 4 particles onto the component of 4 particles of the other state with a similar weight. So this can be computed exactly, and the answer is this. So, but remember, this is not the exact finite L correction. This is just the leading finite size correction, and it's an integral of a logarithm of 1 plus this quantity. And remember, these k are just the analytic extensions of this analytic continuation of the reflection matrices. So, well, so this is very general. So this was done 95 for the generic case. So typically, you will have that this quantity is a very small number. So this exponential. This is typically exponentially small. So you would say, well, why would you keep a full logarithm? You can just approximate this by the integral of this exponential times this product of two matrices, and that's in general correct. And the trace is depicted by this thing, and you have just to do the integral for all values of p, and that's it. So and there is a physical interpretation for it. This is now this is like saying that, okay, the leading Casimir correction to the energy is just because it's like the virtual emission of a pair of particles and antiparticles. They are reflected and they eventually annihilate each other. So this is the leading virtual interaction between the two boundaries. You integrate for all values of the momenta, and that's going to give you the leading finite size correction. But in some cases, this is not correct, this simplification, and it turns out that it's going to be our case, because this analytic extension can have a pole at P0 in some cases. And if there is a pole, so this approximation is going to break down as you integrate, you go to P0 in the integration region. So in that case, you cannot drop the logarithm, and you have to consider the full logarithm in the integral. But it turns out that this integral is dominated by just the coefficient in the double pole of this function as p goes to 0. So the leading answer to this integral is very simple. It's just to evaluate this function in the coefficient of this function in the pole. So there is also a physical interpretation for this. In that case, when there is a pole, it means that your boundaries have the possibility of a mid particle, and if there is a pole also, so essentially you need a pole in the left and the right boundaries, and then if the right boundary can also absorb the particle, this is going to be like the virtual interaction between the two boundaries. So you get the correct L dependence corresponding to a single particle exchange, and then if there could be that these boundaries can exchange many sort of particles, so you should sum to all possible particles that can be exchanged. When L goes,
yeah, eventually you will take a L potential.
Yes.
But here you have to assume L is sufficiently large.
Yes. Well, it depends on the coupling regime you are interested in. I will show you that, for instance, for in the weak coupling limit, this quantity is small, no matter what L is. So L could be finite. So in general, I mean, you're right. So you might need, but then if that is the case, well, maybe this Luchter correction is not going to be valid. What you have to do is to solve the proper TVA equation. Remember, this is just the leading finite size correction, and it's going to be valid as long as this is small. This is small. So you need L to be large In some cases you don't need it, but you would need a coupling to be small. So let's just go to, I mean, those, again, this is also very general. So this was known for, at least for relativistic theories. So let us compute. So for this Luster correction, the only thing we need to know is the trace of this product of two analytic extensions of analytic continuation of our reflection matrices. That's also very technical. In principle, you would, I mean, there is one thing. First, I mean, in this mirror theory, there's an infinite family of bound states that can be exchanged. So you would need to know the exact reflection matrix for all the bound states. The one where we work it out explicitly was just for the fundamental one. So you would need to compute all the others in principle. But it turns out that because of our unfolding trick, there is a simplification. So remember, there was the original picture. In the original SU2/2 square, there were like these magnums were carrying two indices, and when we unfolding this when thinking of this as representations of the diagonal symmetry, they were like a periodic cylinder, and you had we had two particles, and the reflections are now seen as bulk interactions. These red dots just represent the rotation to introduce the Cusp angles. But then it turns out that using crossing symmetry means that we can disentangle the lines by just moving them apart, and then you are left with just these traces. So actually super traces. And if there were no Cusp anomalous dimension, the trace of this, the super trace of this representation would be just 0, and that's okay because the Wilson loop is BPS if there is no Cusp. And when there is a Cusp, it's going to be like the super trace of these rotation matrices, right? So okay, since this is not exactly the bulk scattering, you are left with some factor, which are these boundary dressing factors. It's not that the full, I mean, it's the matrix extractor simplifies, but the overall factor remains. So this trace we need to compute the Luster correction in this Wilson loop case. It's just the product of these boundary dressing phases. So the final result is going to depend on this boundary dressing phase is the correct one, and this super trace of this rotation matrix, which is just the diagonal matrix with phases of the. Remember, we were considering Cusp angles in the geometrical sense and in an internal Cusp angle too. So the answer for this trace is just this. So now what we need to do is just to consider this. Remember, well, I haven't showed this, but I will show you these dressing phases here have a pole as p goes to 0. So we are going to be in this situation in which the Luster correction is dominated by this exchange of a single particle. So let's compute it. Well, I can do it quickly. So this, as I was saying, so this Luster correction is going to be valid if this quantity is pretty small, it's very small. In the strong coupling limit, you need necessarily to have L very large. So this is not going to be related to the Cusp anomalous dimension, but it is a check because, well, you can see that among you have in principle have to sum over all the Qs, but only the Q equal to 1 is leading. So you can compute the leading finite size correction in the strong coupling limit for L very large, and you get this. And then you can reproduce this exact number, this exact angular dependence, and exactly the coefficient by doing a computation of what the string theory energy is when the momentum is not infinite but is very large. You get exactly this energy. So this is at least evidence that the dressing phase seems to be correct. The weak coupling limit is more interesting, as I said, because I mean this is like the dispersion relation of this mirror theory. Well, when you compute this, the exponential of this quantity, you get something like this, and you want this to be small. Yeah, I mean, and since we are in the weak coupling limit, this is small no matter what L is. So this is going to be small for any value of L. So in this limit,
Or I'm missing something, isn't it? Isn't it equal to 1 when L is 0?
yeah, well, you are missing something, and I missed. I mean, actually, what you have here is not L, but it's L plus 1 somehow, because you have an extra factor. You see, when you take L equal to 0, you get order lambda. I mean, here I wanted just to make the point that you don't need L to be large. But it's a good point. Then if you evaluate, I mean, this is complicated, but you can evaluate it just for small lambda and for p going to 0, and this is essentially a double pole that is going to mediate in this exchange. So what you have to do to compute the ground state energy is just to sum, I mean, you have to compute the coefficient. So the overall coefficient is going to be given by this factor, the limit of this when you set p to 0, so the q is going to simplify. And then this is the piece we get for the trace before the previous slide, so 2 previous slides, this one. And then one has to sum for all values of q. So in this case, there is no, this q1 is not dominating over the other ones. So we have to do a full sum over all q's. But it turns out that you could do this sum, and the result is this Bernoulli polynomial. So but now we have just to take the limit. Remember, this is not the full answer. This is just the leading finite size correction. So this is, in this case, it's leading in the weak coupling expansion. So if you wanted to go higher orders in this is going to be the leading anomalous dimension. Higher orders needs to do some TVA computation. But if you take L to 0, the answer just becomes this. And this is exactly what Drucker, Gross, and Oguri got 99 many years ago for the one loop anomalous dimension of the Wilson loop with 2 Cusp angles, the geometrical and it's correct not only for the angular dependence but also the exact coefficient. So this is very nice. But as I said, this is only valid, this is only giving us the order lambda. So in order to go to higher orders, we need to solve the TVA. What we didn't want to do at the beginning, I mean, I didn't want to show how to do it, is to solve the TVA. I'm not going to go through the details. I just, again, going to show again, this is a schematic. But if you, what you have to do is just to consider the TVA in this, let me go back. To the TVA, but you have to the TVA in this periodic system, but then you have to sum to overall states. So you have, and then this projection is going to be dominated by the eigenstate of this Hamiltonian when you have many particles. So you go to densities of particles, and then you solve this using some saddle point approximation. And at the end of the day, you get something like this. So these Y functions are like ratios of densities of particles over densities of holes in this TVA approach. So the energy is given by this an infinite sum of an integral of this log of 1 plus these Y functions, which, as I said before, they have to be solution of certain integral equation in which here enters the dependence on the boundary reflection matrix. So the angular dependence with the Cusp angles enters also here, because one of these reflection matrices is going to be rotated. And this is the convolution with this kernel that is related to the bulk scattering in the mirror theory. So what we were doing before, so the Luchter correction that leads to this when you have a pole, or to this when you don't have, is just approximating the exact solution of this TVA equation by this. Right? This is what you will get if you just dismiss the convolution term. If you dismiss this, which is what we were doing, dismissing that we had to consider superposition with scattering factor if you wanted to do correctly. But if you dismiss that, you think that this is 0, you will get this approximation. This is the Luchter correction. So you can think of solving this iteratively. So this is like the Y0 order the zeroth order approximation of the exact solution to the TVA equation, then you can plug this zeroth order here, compute the convolution, and get from this to a first order approximation of the exact solution, and so on and so forth. So that's the typical way you solve an integral equation. So this is what we have to do if I want to compute the gamma Cusp beyond the leading order in the weak coupling limit, for instance. Again, it turns out that this is not very simple to do in general, because this is a schematic, as Nick was asking at some point. The TVA equations are certainly much more complicated than that. This is like what I was calling YQ before, that only this Y function is going to enter in the energy in the final expression. So here I had to put YA, 0. But its TVA equation is not only coupled to this, well, this is the dressing phase, the boundary dressing phase. This is a convolution with YB0 itself, but then you have convolutions with a bunch of other Y functions, which in turn, they satisfy other TVA equations. So solving this in general is not that simple, not even in the weak coupling limit. What we did was to consider the small angle limit. In this limit, first, because in this limit the TVA equations simplifies, and secondly, because in this limit we know the exact answer. If we take this limit in which the TVA simplifies, by doing this iteration procedure I was telling you here, we did it 3 times, and we computed, well, this was the Luchter answer, or the small angle limit of the Luchter answer, but then the next to Luchter gave us this, and next to next gave us this. But as I said, in this small angle limit, the gamma Cusp is exactly known, so where this h function is exactly known is logarithmic derivative of this Bessel function. You get a ratio of Bessel functions again, and if you expand this at weak coupling, you get exactly these 3 terms we computed explicitly using TVA. So this is more or less all I have prepared. Let me just conclude. So this complicated set of TVA equations are the set of integral equations that can be used to compute this gamma Cusp anomalous dimension exactly for any value of the angles and any value of the coupling in the large n limit, because this is well, in the planar limit is set there, because this is using integrability. We checked that these TVA equations are correct for any angle at leading order in the weak and the strong coupling limit. For small angles, we checked at up to 3 loops that this is also correct. And just as a final comment, I mean, it is true, I mean, they are complicated set of equations, but nevertheless, they are a lot simpler than if you wanted to do a 3-loop computation doing Feynman diagrams. So, well, for the future, what you could be interested in to consider is, well, so I mean, as I said, TVA equations simplified. I mean, I didn't show any detail, but simplify a bit in this small angles limit. But again, it wasn't easy to. You had to work quite a lot to get order by order. While using these localization techniques, the full exact answer is known. So you would expect that if by some means you get a simple exact answer, maybe there is some simplification one is overlooking in the TVA system. And TVA system, the disadvantage they have, they are the most general system. So there is like too much information. So maybe when you are focusing in a particular limit, you have to be clever to just to be restricted to what you need. So maybe there is a further simplification that we couldn't quite see yet in the TVA equations in this small angles limit. You could try to solve them numerically, as it was done for the Konishi operator. Actually, the TVA equations are mostly the same, but with these extra angles here and this extra boundary dressing phase. But apart from that, and certain identification between the Y functions, the TVA are more or less the same. So I expect them not to be much more difficult to solve numerically as for the case in the Konishi. And maybe you can interpolate, you can try to go to strong coupling to compare with known result of strong couplings for the Cusp anomalous dimension. This was the case that Nick was asking at the beginning. So in the twist 2 operators, what you call the Cusp anomalous dimension there, it is a solution of some PES equation, Weiser, in Staudacher. So somehow in this limit, we would like to see that our TVA system reduces to the VES equation. Another interesting limit is phi going to pi, because this is the quark anti-quark potential in flat space. These two limits, which are far from the VPS, are tricky to solve, because you don't have it's not obvious which is the initial, they are not close to a Luchter case, so you don't know how to start. So probably you will need to study them numerically, or maybe some simplification which is not obvious. And finally, to conclude, I mean, in this small angles limit, what we did was to do some computation by two independent ways, one relying on integrability, and this other method using these results known by localization is totally independent of integrability. If something similar could be done for these AVJM theories, that could be very useful, because in AVJM theory, you also have integrable structures, you have a similar symmetry, but when you fix the dispersion relation of the magnons in AVJM, there is an unknown function which is known to be non-trivial. So in N equal 4, you also have a function, but it turns out to be trivially just lambda. In this case, it is not, and it is known to be non-trivial. It is a weak coupling goes like lambda square, and a strong coupling it goes as lambda. So if something like what we did can be done for these two Chern-Simons theories, I mean, some computation, the integrability computation is going to depend on what h is, while the localization result is going to be exact. So maybe this is a way of pinning down what this unknown function in AVJM is. So thank you.
More questions? Yeah.
For the reflecting matrix, we had this symmetry algebra, some of diagonal.
Yes.
How should I think of that?
Pardon?
How should I think of this symmetry?
How?
Yeah, how should I think of the symmetry algebra? acting on that?
How do you find out that this is the algebra?
Yeah, yeah.
So, well, you have just to consider the intersection of what it was, the residual symmetry of the ground state with the symmetries and supersymmetries of the Wilson loop, right?
Can you see it in that reflection picture you've got? By it looks like sort of like break SU to SO or SP in the same way as inserting an orbifold sometimes does in string theory. Can you extract the breaking by thinking about that reflective identification?
So you mean that if this corresponds to making a twisting or something like that? Or?
Yes.
It is, but remember that, I mean, it's not exactly the twisted TVA equations, or because we also have this boundary dressing phase. So this is not exactly just the bulk. So it's the bulk plus something else. So this is that was quite important in our computation. But I don't know if this is the question. So concerning the symmetry, well, maybe we can think of, I mean, the bosonic part of this. Well, I don't know if it's going to be. So for instance, let's think the internal part of this square symmetry. So when you take the vacuum symmetry, so N equal 4 has SO2, 4, the bosonic part, SO6. And when you take the vacuum Z field, so the internal part in this square is just SO4. Right? Because, I mean, you have 6 real scalars and Z is made out of 2 of them. And then out of the original SO6, only an SO4 survives. And then when you take this Wilson loop that picks a direction, now this is for the vacuum. And then for the Wilson loop, you pick one, and you don't have to pick it this. Nor phi 1 nor phi 2, otherwise the Wilson will not be VPS. So you are picking Like let's say in this extra term we were adding in the Wilson loop, like phi 3. And then SO6 is broken to SO5. But this is the SO5 that mixes 1, 2, 4, 5, and 6. And this is the SO4 that mixes 3, 4, 5, and 6. So when you consider the intersection of these two, you get just a single SO3 with that mixes 4, 5, and 6 directions in internal space. So this SO3 is just one of these two SU2s. You can think similarly for the anti-de Sitter part and then also for the supersymmetry. So that's the way you just consider the intersection of these two symmetry groups. I don't know if that was the question.
Yeah.